In this video, we'll talk about Riemann sums, which are used to find area under a curve. If your curve is given by a function, and if the function is simple enough, then you can find the area under the curve or the graph using geometry. So let's take an example. A simple example would be constant function. Let's go ahead and draw our coordinate axis. And let's say we are dealing with this constant function f of x equals 7. So this is 7, and we are asked to find area under the graph between x equal to 3 and 5. So if it is between these 2 points, you can see that this is going to be just a rectangle, and area is simply the length times width. So length of the rectangle is 7, and the width is, this is going to be 2, so you're going to get 14 square units. So for a constant function, we can use geometry. Now, one other case where it's not that much of a challenge is when you have a linear function, which is not a constant one. So linear function would either rise or fall depending on whether the slope is positive or negative. So then, again, let me take some 2 points, call them A and B. So between x equal to A and x equal to B, if I'm interested in this area, then the shape I get is a trapezoid. So I can use the formula for area of a trapezoid, and then I can find out. So this height is going to be f of A, and that height is going to be f of B. And I can use the formula for area of a trapezoid. So these are my bases. These are the parallel sides. So I'm going to take their average, f of A plus f of B divided by 2, and I will multiply by the distance between them, which is B minus A. Now, however, if I don't have a nice function, if it's not a linear function, then it's going to be, well, I would say we can't use our geometry anymore. So say the graph is y equals x square, or f of x equals x square, and you're asked to find the area between x equal to 1 and x equal to 3. Then notice, we don't know any method to find this particular area. And that's where Riemann sums will help us. So here's the idea for Riemann sums. So you have a function. So let's draw our x and y axis, and let's say this is the graph of f of x, and we are asked to find area under the curve between x equal to A and x equal to B. Now, the exact area is going to be hard because this curve is not a straight line. The idea of Riemann sums is to split this into small number of subintervals. The total length of this interval is b minus a because it goes from x equal to a to x equal to b. And if you split it into some number of subintervals, say I'm going to split it into 3 subintervals, which means I'm going to take 1/3 of that length of the interval and mark a point here. another point over there. And then I'm going to evaluate the function at these points. Then I get these particular heights. Now, sometimes I have the freedom to choose a specific point inside each subinterval, and sometimes the problem will tell me which point to choose. So say if I choose the midpoint of each subinterval, so I'm going to go in the middle of each subinterval, choose that, and then if I evaluate the function at those midpoints, then I get certain height. And what I'm trying to do is I'm going to pretend that in this subinterval, even though the graph is curving, I can assume that this is constant. And if this was a constant function, then I'm going to get this particular height for that subinterval. And here it's going to be this. So what I'm getting is, and then I'm going to evaluate area under this rectangle. Area under this rectangle. And for this, I'm going to draw another rectangle. So as you can see, I have approximated area under the graph. I'm not going to get an accurate answer, but you can imagine that if you increase the number of subintervals, then these widths are going to get really small, and then you get more and more accuracy. But it would mean a lot more work. So for simplicity, I only split it into 3 subintervals. And then notice how I can get area under this graph. So area of the first rectangle is going to be its length, which is, so let's call these representative points, the midpoints in this case, as x1, x2, and x3. So length of the first subinterval is f of x1, and its width is b minus a, the total length of the interval, divided by 3. So this is the area of the first rectangle. What's the area of the second rectangle? For the second rectangle, we evaluated the function at x2. So that's going to be our height, and it has the same width. So it's b minus a over 3. And for the third subinterval, the height is f of x3. And the width is again b minus a over 3. So as you can see, b minus a over 3, this is the width, which is the same for each of the subintervals. So we can factor that out and then write down f of x1 plus f of x2 plus f of x3 in parentheses. So 2 things to pay attention here. The problem will specify which representative point you need to choose. If you're asked to use midpoint, then your x1 is at the midpoint of each subinterval, is at the midpoint of the first subinterval. Now, sometimes the problem might say find the left Riemann sum, which means the representative point is at the left endpoint. So x1 would be at the left endpoint of the first subinterval, and x2 would be at the left endpoint of the second subinterval, and x3 would be at the left endpoint of the third subinterval, and so on. So, and also the number of subintervals would be specified. Usually, if it is an exam problem, then the number of subintervals would be really small. But if you are using a computer or some calculating device, then you may be asked to use more subintervals. So two things, the value of n and also the representative point. Now in general, how would you find area under the curve? Well, it's going to be simply, remember, it's 3 because we use 3 subintervals. But if you use n subintervals, then it's going to be b minus a over n. And inside the parentheses, it's all sum. It's the sum of function evaluated at all the representative points. So I can use a summation notation, b minus a over n, and I can index with I and then say it's f of xi star. Or I could have just said f of xi. Yeah, let's just say f of xi. So this is the formula for the Riemann sum. And let's actually work out an example. So let's find area under the curve. So here is the exercise. Find the area under the curve f of x equals x square between x equal to 1 and x equal to 3 using 4 subintervals and using the right endpoint in each subinterval. Or sometimes the problem might just say find the right Riemann sum. All right, so let's draw a rough picture for x square. We know that it's a parabola. So let's draw a rough sketch of a parabola. F of x equals x square. And here is x equal to 1 and x equal to 3. So we need to figure out the area under this graph. Now, since n is equal to 4, we got to split this into 4 subintervals. So width of each subinterval, sometimes it's denoted by delta x, is 3 minus 1 divided by 4, and that's 2 over 4, which is 0.5. So if it is 0.5, that means the first subinterval would begin at 1 and ends at 1.5. The next one ends at 2, and the next one goes to 2.5. So we have these 4 subintervals. 1 to 1.5 is the first one. 1.5 to 2 is the second. 2 to 2.5 is the third. And then 2.5 to 3 is the fourth one. And also we are told to use the right endpoint, which means for the first subinterval, x1 is going to be here, which means I'm going to find area of this rectangle, which you can see is actually overestimating the area under the graph. For the second subinterval, we are going to use this endpoint. So that's going to be the area. I'm going to alternate in blue and red. And then for the third subinterval, our representative point is 2.5. So that's the height of the third rectangle, which is going to be that. And finally, for the fourth subinterval, the representative is here, which means the height is f of 3, which is that. So when we evaluate the Riemann sum, so area I can write down is approximately 0.5. That's the width. And then we are evaluating. So let's just go ahead and write down f of x1 plus f of x2 plus f of x3 plus f of x4. And f of x1 is 1.5 square plus, because it's f of x equals x square. F of x2 is 2 square. F of x3 is 2.5 square. And f of x4 is 3 square. So that's going to be 0.5 times 2.25 plus 4 plus 6.25 plus 9. And I calculated it. It came out to be 10.75. So that's the area under this graph.